And again, welcome to today's webinar, Designing for Scale, 3 Steps to Optimal Data Performance Using DynamoDB and Redshift. Our presenter is David Pearson, Lead Business Development Manager for Amazon DynamoDB at Amazon Web Services. David, you have the floor.
Thank you, Carrie, and welcome to the webinar. In Designing for Scale, we've decided with this webinar to focus on digital advertising it's been a very highly adopted industry for DynamoDB and Redshift. And so we decided to talk about designing for scale and relate that to the types of implementations we're seeing in that particular industry. I want to cover a few things. So we're going to start with a very brief introduction to database services, and then I'm going to walk through the main players and add it in the context of how they are employed in an ad-serving environment. So just to start with, database services, it's one of the foundation services of AWS. Along with compute and storage, databases are really the foundation of an application. And what we focus on at AWS is choice. So the first choice you have is, of course, to build your own on EC2 and EBS and so on. The other approach is to use a managed database service. And this is, of course, reflective of the sort of effort it requires to maintain and scale and to build the databases in the cloud or anywhere else. So the 4 primary services that we have, Amazon RDS, Amazon Elasticache, DynamoDB, and Redshift. So RDS is the relational database service, MySQL, Oracle, and SQL Server, really designed around making it easy to provision, scale, and manage those databases for traditional applications without having to change the code. Elasticache, we've recently announced Redis support. Elasticache supports Memcached as well. And what that provides is an in-memory cache for optimizing heavy read scale events. Redshift and DynamoDB are going to be the focus of today's session. So with DynamoDB, it's a non-relational data store designed for high velocity, very fast transaction, low latency, high performance transactions at any scale. Redshift is a warehouse, an analytical data store designed. It's relational and it's designed for very large data volumes and very large queries operating against those. So a key attribute of the managed services is the recognition of effort and the differentiation of effort. And so in provisioning, managing, and scaling databases, what we aim to do with these managed services is to automate the low-level or the housekeeping or undifferentiated effort associated with owning these databases. The idea is to allow developers and architects to focus on their applications and their infrastructures, making them better, faster, and so on. So by automating that, taking that pressure away from the administrator, the database services are there to improve the performance without having to worry about dealing with low-level architecture and so on. When we talk about the big data services, the core of the core services in which people are building big data support infrastructures on AWS, it comes down to really 4 primary ones, which is EMR, or Elastic MapReduce, which is a managed Hadoop service. Object storage in S3 is a fairly ubiquitous way of moving data in and out of the internet, and of course storing it and staging it for different purposes within the environment. DynamoDB is really focused around real-time. It's a transactional data store, so very, very high ingestion or consumption patterns where the workloads can be unpredictable, but certainly at scale. Anything at scale is a challenge for real-time. And similarly with Redshift, that scale becomes a function of doing large queries against very large data sets. The benefit of that is, of course, online analysis and reporting. You get deep understanding into your data. So let's focus on DynamoDB as a quick intro, so we can describe a few of the main virtues of the service and why it appeals so much to our digital advertising customers who have adopted DynamoDB quite aggressively. And then we'll flow that into an ad serving pattern so we understand exactly how people are using these. So DynamoDB is a non-SQL, non-relational database. So what that means is it does not have the relations, the joins, and so on of a traditional relational store. It is built around predictable performance as a cornerstone to its design philosophy. So when we enhance and add different capabilities, it always comes back to have we maintained our performance profile. So it's extremely important that we do that. Scalability is a primary concern of most of our customers, and the ability to scale seamlessly and massively is an attribute of DynamoDB that sets it apart from many different options. Finally, DynamoDB is a service, a fully managed service. It eliminates all the low-level effort and administrative tasks associated with running, scaling, maintaining a database in the cloud. Now, Amazon's path to DynamoDB, DynamoDB is a function of a rich heritage, which started with relational, as most workloads do, but recognizing that as workloads scale, performance degrades, and unfortunately that can happen exponentially. So the problem with scale is, of course, there is an expense associated with and a cost associated with scaling to extreme degrees, but at some point there's also physical barriers to which a relational database, beyond which a relational database is unable to scale. So Amazon basically their path reflects the journey many of the customers are now taking. It starts with using a relational database for all use cases by default, where we treated relational as a Swiss Army knife. Hundreds of applications. Unfortunately, for those that needed very high scalability, there were limits that relational imposed upon those workloads, and as a result, availability became a challenge. And I mentioned the cost as well. So what was launched was an internal project to really determine what was needed in a data store to overcome those problems. And this culminated in a technology called Dynamo, and subsequently a white paper called of the same name that was released in 2007. So the Dynamo technology is basically a distributed hash table with consistency management. Very specialized, simple use cases, very, very high scale, but still a technology. Only available within the organization. That was released later, a couple of years ago, as DynamoDB. So DynamoDB as a service, and I should kind of mention that the difference between the white paper and DynamoDB is about a 10-year gap there. And so DynamoDB is a substantial evolution from that original design. It is not the same design. It's far evolved from that. But the point about DynamoDB's core value there is as a service, it delivers many of the values that are impossible to achieve with the technology. And so we'll talk about the consistency, the durability model, because those are core elements in why digital advertising companies are adopting DynamoDB. So when we look at the primary users for DynamoDB, and the fonts go a bit funny here, and I apologize for that, but we focus on developers, operations, and users. There are three different types of stakeholder effectively in applications built on DynamoDB, and they have different requirements from their applications. So in the case of developers, it's really about fast application development, optimizing the time to build new applications. And so this is a key reason a lot of our customers have adopted DynamoDB. You may have read on blogs recently the Dig reader chose DynamoDB because they only had a few weeks before Google was retiring their reader, and they decided to build their version of that. It was just impossible without adopting a managed service, because the effort required to just build the infrastructure and then sustain that and scale that would have meant they had no time to effectively build the app. So fast application development time is really facilitated by the flexibility of the data model, very simple API. You don't need to worry about partitioning schemes and strategies. You simply build around your hash and go from there. High-scale queries with the delivery of local secondary indexes make it very performant and very flexible. And recently we announced the ability to develop local DynamoDB on your laptop. From an operations perspective, most of our users have high-scale demands, and this is where DynamoDB excels. And the ability to do at any scale, essentially administrative-free operations is very compelling. A cornerstone to this is the concept of provision throughput. And so DynamoDB implements a request-based capacity provisioning model. Okay, so what that means is instead of servers, memory, and storage, DynamoDB users request throughput. And then the back-end automation layer takes care of the rest, i.e. the servers, memory, and storage. So you can scale reads and writes independently, which is great for different access patterns. It might be a big ingest process at one time, and then that may turn to a high read the next. So these can be scaled up and down independently to give that sort of flexibility. So for example, a large data load may occur each day, but then the write capacity dials down while the read capacity comes up for steady state. So what's significant about this approach is, and especially as a service, is that scaling up is done. It triggers automatic repartitioning, reallocation of services and capacity in the background. That is abstracted from the user. What the experience looks like is you'll get the capacity you reserved while the new capacity is being provisioned. Once that has been completed, then you will see that new capacity. So it's seamless. There's no impact to performance, and there's no impact to availability during the scaling process. So that's very compelling for any high-scale application. The third element of DynamoDB that's really important is really the experience of the users of applications built on DynamoDB. And this can be described best as durable low latency. So with durable low latency, the concept is very simple, is that writes, and it's not a dissimilar concept to a relational database where when writes are written to the database, they are essentially have guaranteed durability. That's different to a lot of NoSQL options people have today, in which they are either cached temporarily or permanently in memory, which doesn't give the guarantee that the write is actually durable if they're in the event of some infrastructure event. And so writes are replicated continuously and they are spread across 3 availability zones at any point in time. When we reach quorum on any 2 of those for a write, the write is acknowledged. So it's not just replicated and redundant in multiple AZs, it's actually persisted to disk. And the whole stack of Dynamo is built on custom solid-state devices. So it's extremely low latency, very high throughput. Reads are strongly or eventually consistent. There is no latency trade-off in choosing that. The throughput is actually cheaper for eventually consistent reads, but latency remains very consistent. And a recent announcement with DynamoDB is DynamoDB Local. What this new tool provides is disconnected development. So we've had a lot of input from our customers who want basically the kind of LAMP stack model, the traditional approach where everything's on the laptop and the whole development and early test cycles can be performed in that environment. So full API support, downloadable now as a local development option. So we have plenty of customers adopting in DynamoDB in the digital advertising space, and a lot of it comes down to really 3 or 4 factors. Scalability, of course, the performance characteristics, but the ease of effort and, in fact, the cost of a well-designed system on DynamoDB can be extremely low. You can see Adroll recently just tweeted about how they are actually spending more money on food than they are on the service itself. So they've taken advantage, for instance, of reserve capacity, which is a great way to further reduce cost. So when we talk about putting this all into an ad serving or digital advertising context, let's walk through a brief scenario, a highly optimized scenario where A visitor is visiting a web page, and we'll see how customers are employing DynamoDB to service those back-end requests. So it's kind of a 1, 2, 3, 4 step process here. Once the visitor loads the web page, then that page issues a request to the ad servers. So they're dedicated servers on EC2. And what those ad servers will do is issue requests to the back-end data store. And that data store obviously needs to be super fast, like DynamoDB. Durable is obviously highly important too. The point there being that the ad comes in, the request comes in, is matched to a profile, and through this interaction, then now the ad server knows which ad to serve back to the visitor. And so that can look inside DynamoDB in a very simple table construct. So within DynamoDB, the predominant lookup for these sort of patterns is by the primary key. We do have local secondary indexes which enable index lookup, but these are fairly simple data structures. They just happen to occur at very high volume. So with that in mind, it's a perfect implementation to put it into a NoSQL store like DynamoDB. So DynamoDB requires one attribute to be defined as a hash, and this is named because it is used to distribute the data amongst the cluster. So good broad distribution of data requires obviously uniqueness of the hash key. But by adding a range key, DynamoDB users can also build a degree of queryability to the data. So a range key will form a unique composite primary key with the hash key attribute, but the rich queries that can occur against the range key are enabled by both hash and the range construct. And when we talk about query, you can talk about the most recent items for that hash, the top 5, or items between specific dates. So these are very popular ways of implementing the actual data level, the schema level implementation. Now, in an ad serving context, the real-time bidding is becoming a super fast growing corner of the market, which is very difficult to achieve because of the really high demands for really low latency. So when we talk about real-time bidding in the back end, there's additional processes going on in which the ad isn't just served; it's actually there's an interaction going on with an exchange, with a bid platform. So that additional interaction obviously consumes time. So that has to occur really quickly, where there's a bid and an acceptance, whether the bid is won or not, before the ad can be placed. So DynamoDB has been employed in this sort of environment because as a really low latency and durable back-end data store, not only can it handle the relatively light load of doing ad serving at scale, but it can implement on top of that real-time bidding construct where interactions with other third parties can occur in very, very low latency. So when we extend this further, what happens to the ads? So the URL comes back as serviced by DynamoDB. Impressions so the ads are then loaded from CloudFront, which is an edge service, basically cached physically close to the receiver of, or the requester or the visitor in this case. CloudFront is a distributed CDN, content delivery network. So images, videos, and so on can be quickly delivered delivered globally to the user. Impressions that have been served to the users are then registered, captured in the CloudFront logs. So that makes a great downstream analysis, and these are staged into S3 for that sort of purpose. So going forward, when in enhancing this sort of this basic architecture we've got, what we've done is added here elastic load balancing and auto scale with multi-AZ. So what is important about that is the ability to kind of plan for high growth or business success, but also maybe a great deal of elasticity between peaks and valleys. So elastic load balancer will enable you to spin up a lot of additional ad servers and then of course shut them down if the demand warrants it. So ELB can operate with EC2 instances across multiple AZs. That's a key part of giving increased data protection as well. where if there is some incident with the ad servers in one availability zone, then those in the other availability zone can take over seamlessly. And so that's how a lot of people build, and that's how we recommend people build protection into the app tier. So what further happens then with the visitor, obviously if there's the impression served and then they click through, the same sort of architecture at the back end, which is the click-through request is received and then basically logged into S3. So all of this data is being built up inside DynamoDB, inside S3, perfect for flowing then down into an analytics process. So this is where Redshift comes into this sort of design. And so let me just spend a couple of minutes introducing Redshift, and then we'll get back to the ad serving approach. So Redshift is a relational data warehouse. It's a relational database. Underneath the covers, it's a columnar data store, which basically optimizes it for very large queries against very large data sets. So it's MPP, massively parallel, distributed everything, shared nothing architecture that can scale to petabytes. Again, it's a fully managed service, so Redshift will, of course, take away a lot of the effort associated with owning and operating a large-scale data warehouse. A cornerstone of Redshift's performance, of Redshift's value, is the performance profile. Redshift is designed to be extremely fast, extremely performant, and it does this by by reducing the I/O, and dramatically so. So in using direct attached storage and large block sizes, fairly standard, but beyond that, it's a columnar data store which has also a very high degree of compression. What columnar means is, of course, the data is physically stored on the disk in alignment that will give it extremely fast scan capability across billions of rows. So it's not designed for row-by-row access, but by column aggregation. Zone maps is a capability in Redshift that enables, with a good, well-designed sort key, the ability for predicates that limit data requests to be basically skipping I/O blocks and get to the data a lot faster. So all of this is ways of dramatically improving the I/O profile of requests occurring against Redshift. Redshift is built on an architecture where everything is parallelized and everything is distributed. So this goes from load, query, to resize, backup, and restore. These are the sort of things you can do in the cloud that are very difficult to do on premise. For example, resize is essentially a one-button selection. You select the cluster that you want to resize to, and then you ask the resize process to go forward. What Redshift will do is provision a whole new cluster of the requested size, and it will in the background stream disk to disk all the data from one to the other. And during that time, the original cluster will be in read-only mode, but the useful part of that is, of course, your reports will continue to run, and there'll be very slight degradation during that process. So when the resize is complete, a brief DNS flip will occur where the new cluster now becomes your primary endpoint. Redshift is backed up and restored. It's backed up by S3. What that means is you've got an extremely durable back-end data store protecting the data from the local disk. So the local disk has protection within it. The cluster has protection within it where we store multiple copies of the data. So when disks die, as they will, we have a secondary copy live and available for access while the disk gets rebuilt. But all the data continuously streams into S3 as well to give additional protection there. In terms of security, Redshift is extremely secure with the VPC protecting front end. You can only basically see the leader node, which is the gateway through which the client tools connect. The back-end services are only available through API and otherwise not visible. So data is highly protected, and of course it's encrypted in flight at rest as well, including the backups. So with Redshift, there are two node sizes, the extra large and the 8 extra large, and you can start very small with the extra large, which is basically a 2 terabyte allocated disk. You can start with one of those, or you can cluster them together up to 100 nodes. I think that's actually 64 nodes. The 8 extra large can cluster from 2 to 100 nodes, which takes you up to 1.6 petabytes. So at any point with that resize working the way I described, you can basically move from one size to another at basically the request, the click of a button, and then a slight time delay while that resize occurs. Very important to queries, optimizing queries inside Redshift once they're there is the ability to monitor query performance and then drill down into those queries and understand what they look like, explain the plan, and to see where bottlenecks occur in poorly formed queries and queries that are just processing in unusual ways. So Redshift provides a full monitoring interface as well as the ability to keep drilling down into the explain plan. So Redshift works with existing BI tools. What that means is we have these are tools that have already been certified against Redshift, but the connectivity to Redshift is via a Postgres driver. So what that means is any tool that supports the Postgres driver will actually support Redshift through a JDBC or ODBC connection. And so we've got a lot more connectivity than is listed there. Basically anything Excel included or platforms that are not listed on the screen there will also work seamlessly with Redshift. Redshift is also priced very competitively. It's designed really to enable users to bring all their data into an analytics world, not just the data which is considered the most important. We encourage a lot of experimentation, bring data in. If it's not useful, then you can obviously just throw it away. Clusters can be spun up and shut down very quickly. And so from 85 cents an hour for on-demand, that scales up to $999 per terabyte per year, which is extremely cost-effective compared to other options. So some customers on Redshift, what they're seeing is, as designed, very high performance, very low administrative effort, and very easy to provision and deploy new clusters to satisfy the use cases. So let's go back into the analysis, into the ad serving use case, and look at how analysis extends the sort of things we've captured inside using DynamoDB and S3 as the primary containers for data, and how we would extend that to include both MapReduce and Redshift. So the architecture now extends where impression data, click-through logs, and so on, basically they flow through EMR, Amazon MapReduce, Elastic MapReduce, which is a managed Hadoop service. And that data is used then to update the profiles of and update the data that is accessed through the real-time interaction with the requests coming in. And so that updates profiles in DynamoDB as well as other campaign information and so on. So that data is kind of curated periodically every few hours and then and refreshed into the database so that subsequent activity against those tables will use the latest data. So there's always pressure on that process to be more and more streaming, more and more real time. So what we're seeing is smaller data sets coming through and then processed a lot faster. So the advantage EMR provides in that is, of course, you can spin up larger clusters to get things done faster and then shut them down, so you only pay for what you use. Spot instances are also very popular in accelerating throughput, the processing of data at a very low cost. Now, how this works with Redshift is Redshift is also used for a lot of this sort of analytics, and what we're seeing more of is it's being used in both a semi-real-time function, for example, figuring out bid optimization or taking impressions and requests from the primary database, analyzing it to understand if there are characteristics we can tweak about the user profile. So these happen predominantly in MapReduce, but they can also flow into Redshift or even occur in Redshift. This comes down to personal preference as much as anything, and one thing we do advocate for is that you really look at the use case and adopt the best tier, the best processing technology for both the experience of the team who are tasked with this, as well as that which services the use case best. At medium to low scale, there will be probably a very little difference between these as options, but as things scale up, obviously the better choice will become more cost effective. So how are customers optimizing with Redshift in exactly this sort of environment? What we're seeing is, for example, in bid optimization is essentially sets the objective of driving qualified users to advertisers' sites. So the qualification process is really important. So they're not just serving up ads and without having some sort of reference ability, some sort of understanding of what the customer is interested in. That understanding of the customer is very important. And so the inputs to these are both from a storage perspective, the logs that come in from the servers, impressions, click-throughs, and so on, as well as third-party data. And this gets blended and can get loaded directly into Redshift in one case. It could also flow via EMR if depending on the structure of the data. But then things like bid history and user history also flow into Redshift. All this data exists inside Redshift and then in separate tables which are then joined, and then the collaboration is done between them. So data patterns that emerge by blending this data together using SQL queries and BI platforms and so on makes it very easy for the data analyst to understand with all this complexity of data, very easy for them to understand what sort of bids will produce the best results. In a similar approach, optimizing costs, which is really focused on the revenue on advertising expenditure. When we're issuing ads, what is the sort of revenue that generates, and if we tweak things, how can that be improved? So again, you've got impressions driving a lot of that, but blending with third-party data for things like behavioral analysis, contextual analysis, and so on. Combining that with the history, the actual history of the request history from customers, and then flowing that through MapReduce for an enrichment process. So basically blend these data sets together and then store it in Redshift. The value of Redshift that Redshift provides is, say, it takes a lot of the pressure off MapReduce because it doesn't have to process the entire data set every time. It can do it incrementally and then flow the data into Redshift, which contains the full data set and of course is fully accessible online and accessible via SQL-based tools. And so the relationship there between the four big players in the big data stack it becomes very intimate, and the interactions between them enable these sort of data flows to occur very easily. So when we look at what is being done in these markets, especially digital advertising, and how Redshift and DynamoDB in particular are being used, but certainly MapReduce and EMR and S3, we kind of can distill from this 3 steps to optimal performance. The first one is really to focus on the full life cycle of data. We've seen a lot of customers make the mistake of looking at just the first phase of data in isolation. That's not a mistake per se, unless the decisions associated with that don't lend itself to processing the data downstream. So sometimes the connection between different parts is the biggest challenge, not the pieces themselves. And so, in focusing on, let's say, phase 1 of data ingestion, processing, ad serving, and so on, we also recommend just stepping back a little bit and understanding what you want to do with this data later, because those sort of decisions are very important in knowing what integrates well together, what flows easily down, from an operational sense or an analytical sense. And so that's extremely important to get a higher perspective on that. Associate that also with data volumes and, of course, SLAs. Things like latency, availability, and durability, extremely important. Some data that can be cached in memory because it's already protected in another way, it is just a copy of that data, then a cache might be the perfect way to service that data, to expose that data to consumers or to back-end processors. So, bearing in mind all of these things across the full data lifecycle and gets to the timeline of each interaction and consumption pattern is very important. The second step is really to focus on really leverage the specialization that is available now. We're seeing people move away from the database as a container concept, or database as only a container concept, into a one where focusing on how the data needs to interact with different services means I may use one or two or multiple different data stores or even processing layers. So for this sort of approach, we really ask customers to not just look at the overall picture and say throw it into a relational database, which is kind of the old approach, because the SLAs, the latency requirements, availability, and so on may actually preclude that from being a good idea. It may be a great idea for some of the data and is likely to be for some of the data, but for other aspects of the data, it may be the wrong choice. And so what we'd like to do is kind of typify the core value of each of those components in the big data stack. DynamoDB focused really about real-time transaction processing, durable low latency being its kind of key attribute in delivering a consistent user experience. Redshift is the enabler of online reporting and analysis. So online all the time, huge data sets, large queries can run very quickly in Redshift. EMR's principal approach here is to take unstructured data and blend it with other data to do very comprehensive enrichment, and often that flows into Redshift to persist the data for downstream further analysis on optimization and usage patterns and things like that, or to flow it back into in fact to flow it back into stores like DynamoDB for just enriching that things like the user profile example we described. S3 in this sort of context is a perfect data staging area where it could be used as the archive, if you like, data of record, as well as the operational data store for data that is in between different stages or different processing processing stages or storage options. So data in S3 can obviously flow downstream into an archive service like Glacier for lower cost offline storage and still retain that full access to the data set at a very low cost. So these are the approaches we suggest in terms of leveraging specialization that is available. The final step is really to focus on the access patterns and optimizing the access patterns. So the main things we see when customers, the main tips we kind of provide when customers are building these sort of environments on DynamoDB and Redshift in particular, is really we focus them on focusing them on efficiency, maximizing the efficiency of the way that their data interacts with the patterns, the access patterns, the queries in particular, but also there's updates and inserts to consider. So in DynamoDB, this comes down to, in large part, minimizing the payloads. So not having enormous items that move with every interaction, but maybe minimizing that in a smart way by aligning to the patterns themselves. So counters, for instance, incrementing should be done in isolation, not against a full payload. So that's a real part of optimal design that we found has saved a lot of people a lot of money when they've done it right. And of course, separating hot data from cold is kind of the other tip, the other place where time spent is very well rewarded. DynamoDB is great for hot data, but again, you're paying for throughput. So cold data, you don't really want to pay for throughput on cold data. So separating those, especially for time series data, we've seen customers build time series structures where it's become extremely cost effective, and oftentimes the aged out data flows into Redshift very smoothly and then can be deleted from DynamoDB at a very low cost by just dropping the table, which is always cheaper than deleting all the items in it. Inside Redshift, best practice is really, we always emphasize a good distribution and sort key selection is really important, because this really determines how local joins are and then how quickly you can skip blocks when queries come in. Sometimes there are some uncertainty over which are the optimal keys to choose for these. So what we strongly advocate is spend a little more time testing them, have a benchmark against which these can be tested, and then just try them out. So often some of these changes won't have a material difference, but when they do, it could be substantial. And we've seen a lot of this, especially in the early days of Redshift. Before we were fully launched, we had a large limited preview running, so our documentation wasn't fully fleshed out. And so we worked with a lot of customers to ensure that their distribution and sort key selection was optimal. And once that was made, they were seeing many times the improvement compared to prior to that. Efficient ingestion is also a good place to spend some time, because once you get it right, it makes up for everything else. Spending a bit of time there, figuring out how DynamoDB data flows into Redshift. There is a one command copy for that, and it's really optimized for time series data, where it's a table-to-table mapping, and that works highly parallel, and it will integrate with the read capacity in DynamoDB, so it won't consume all of the available capacity. It'll consume just the percentage of it that is nominated. In S3, same sort of approach on reads, highly parallelized, direct read from S3 to the back-end cluster. So extremely fast ingestion, but what is important there is to make sure that the structure of the data lends itself to optimal ingestion patterns. So that's most of what we have today. I've just put some resources on the screen as well as a final, maybe some links that are of interest. We've recently launched a best practice how-to and tools page in DynamoDB, which is just /resources from the DynamoDB page. And on that page, there is a testing area where you can download DynamoDB local. We always recommend that. It's been highly requested, and obviously a lot of development occurs on laptops. So that's a great area to look at. In Redshift, we've seen a large degree of popularity for the best practices, and so we constantly refer people to those. They answer most of the questions about efficient data loading, ingestion, getting data into Redshift, as well as query patterns and designing the tables, including distribution and sort keys, but in addition to that, other ways of ensuring that queries will run optimally. So we recommend these resources to you. And that's all we have for this morning. If there are questions, you may have already asked them, please let me know. There are some questions here. So I'm going to jump to a couple of questions, and I'm also going to put the survey up after this. So I'll put the survey up while the questions while I'm covering the questions. So question, let me just enlarge this. Do you have any sample code that we can use to create something similar to what you are showing? Great question. We're working on it. This is a function where PowerPoint is ahead of. It's easier to code in PowerPoint than it is in templates. But yes, we're working on that. So we do want to be building templates that we'll make available. You may have seen in things like DynamoDB that we've started to launch libraries that make it easy to interact with the service. We will be extending that also with different sort of samples and fast start approaches to building things. And yes, the webinar has been recorded, and the slides will be available in SlideShare, as well as a recording of the voice and video as well made available for you. Is there a publicly available application that I can subscribe to see DynamoDB and Redshift? That's a really good question. We don't have one on display ourselves. What we've done is work with a lot of partners on that, but the partners tend to be more on the Redshift side, say, showing their BI tools. So you get some great demonstrations by Jaspersoft and Tableau and others. On the DynamoDB side, it's a little less popular because DynamoDB is more of an embedded application. So from our perspective, no, there's not, but we can keep a lookout for that for you. There are a lot of I do direct you to that resource page for DynamoDB. We're trying to populate that. That's not just our resources, by the way. So for example, things like auto-scaling, which we don't have in DynamoDB today. There is a library there, Dynamic DynamoDB, which we list on that page and we describe and we link to. So it's a great way to get resources to build your skills. I think that's most of the questions that we had. So we'll leave it at that for now, for today.